My name is Sushrutha. I am 4th year BSMS student. Hello. I am doing a semester project under Krishna Kaipa, and the topic is representations of symmetric groups. So I am referring to a book called James Kerber, written by James Kerber. The name of the book is Representation Theory of Symmetric Groups or something. And so he has done some work in 2 pages, okay, 2 or 3 pages, okay, 3 pages of work. That will be my topic for the talk. I will take like 1.5 hours. So it's so densely packed in that section. So that will be what we are doing. First, let's start with what you know about symmetric groups. Okay, I will define what alternating groups are, starting with the facts you know about symmetric groups. Okay, so Sn, that's the notation. It's a group of permutations. What is a permutation? It's a bijection. Bijection from a set of n objects to the set of n objects. Take it to be letters or numbers, doesn't matter. Let's take a set 1, 2 till n. Call this set capital gamma. Look at all the maps from gamma to gamma which are bijective. How many elements do we have here? N factorial. That's basically the number of ways you can arrange n many objects. So the size of a symmetric group is n factorial. Now what is the group structure on it? It's the composition. If you think this as a function from a set to a set, composition of the functions will act as the operation with which this group Sn will become a group. The set Sn will become a group. Sorry. Okay. Now you know this stuff. Now let's talk about conjugation. Some group theory terminology I want to revise today. Do you know what conjugation is? Conjugation. Okay. Conjugation is an action of a group on itself. Now take an element G from a group capital G and take another element H. When you multiply H and H inverse like this is called conjugation by the element H. Now what we are doing here today is we will see what happens to each permutation when you do conjugation to it. Before doing that, we will talk how do you represent. Okay, this represent is not about representation. How do you depict each element in Sn? So you guys will know, right, cyclic structures, writing in cyclic structures and all. Today we will, I want to tell about that for first few minutes, then we will start. Okay. The worst way to write this bijection is writing like this. Let's talk about some S7 maybe. 1, 2, 3, 4, 5, 6, 7, and writing the numbers where it goes, like 6, 5, 2, 3, 1, 4. What is missing? 7. Okay. This is one way you can write one element of Sn. What does this mean? 1 goes to 6, 2 goes to 5, 3 goes to 2, like this. That's the meaning. But here you don't get much information, so there is a better way to write this. How do you write? Using cyclic notation. So what you do is start with one element. Start with 1. Where is 1 going? 1 is going to 6. Write 6 here. See where 6 is going. 6 is going to 4. Write 4. Now where is 4 going? 4 is going to 3. Write 3. Where is 3 going? 3 is going to 2. Write 2. Where is 2 going? 2 is going to 5. Where is 5 going? 5 is going to 1. 1 is the first element, so close the bracket. Now start with some element which you didn't touch yet. That's only 1, so you will start with 7. Where is 7 going? 7 is going to 7 itself, so you close the bracket. This is the another way to write every permutation. Like this you can write, okay? Now this is another way to represent, okay? Now, in both the ways, let's see how you can write the inverse of this element. In this way, it's very simple. You just put this row on top, put that row on the bottom. That's it. If you swap, start with 6, 5, 2, 3, 1, 4, 1, 2, 3, 4, 5, 6. A good thing is what you can do is you can arrange it in ascending order, but that's not needed. Who cares about that? So this will be the inverse, and you can easily see that pi times pi inverse is identity, right? So 1 goes to 6, 6 comes back to 1. So it's identity. So that's why that's the inverse. In this notation, how do you write the inverse? You write each cycle in the opposite direction. That's it. So 7, 2, 3, 4, 6, 1, 7 stays as it is. So this is how you can write inverse. 5, 5, well, thank you. 5, 2, 3, 4, 6, 1. Now, this will be the inverse. Now, let's just verify whether it's inverse or not. What will pi do to 1? Pi will send 1 to 6. What will pi inverse do to 6? 6 will go to 1. So 1 will map to 1 itself. Similarly, every element will map to that element. So pi inverse will be identity. So this will be this is how you write the inverses. Now, let's see what will happen when you conjugate an element with another element. Now the real stuff begins. Now what I claim is when you conjugate, then the cyclic structure doesn't get destroyed. It is preserved. So I will just show it how. So let pi be write pi in cyclic notation. Many cycles, each cycle containing some elements. Let me just write here A1, A2 till AL, where L is the length, okay, length of a cycle. Here B1 till BL2, let this be L1. Similarly everywhere, okay. Now let's conjugate this. So what happens? Let sigma be another permutation. Let's see what happens to sigma pi sigma inverse. What does this do? What is your guess? So I will tell what happens. It will be the same cycle, but everywhere sigma is acting inside. Like rather than A1, A2, A3, it will be sigma A1, sigma A2, sigma A3 like this. I will just prove why I am claiming like this. Let's see what this guy does to sigma of A1. What will happen to sigma of A1? Tell. Sigma of A1, when you apply this, sigma inverse and sigma will get cancelled. So pi acts on A1. What will happen when pi acts on A1? What does pi do to A1? A2. It will send it to A2. Now sigma will act on A2. So you get sigma A2. Correct? What will happen to sigma A2 when you apply this? Sigma cancels. Pi sends A2 to A3. Sigma sends it to sigma A3. Sigma A3. Let's complete this. At the end, you also get sigma A L1, right? Now what happens to sigma A L1? Sigma inverse cancels the sigma. Pi of A L1 will send it to A1 itself and sigma A1. So this will come back to this guy. So this is the cycle you get. What is the length of the cycle? Still L1. So the cyclic structure. So we'll take any permutation in S7, multiply that here, multiply the inverse here. You get the same structure. What I mean by the same structure is you get the same 6 cycle and a fixed point. That's what you get every time. So you know the definition of conjugacy class. I'll just define it. Also the notation is important. Today I'll be using Cl. Looks like chlorine. Every time today is like chemistry terms. Ambivalent was the title, right? It sounds so chemistry term, but it's not, okay? So Cl is for class. There's a reason why I'm writing like this. Of an element pi, and I will also write and what group we are talking about. Today we are talking about 2 groups, right? Just for clarity, if I write S at the as a subscript, it's the conjugacy class in symmetry group. If I write A there, it will be conjugacy class in alternative group. That's right. This is the notation. This is the set of all sigma pi sigma inverse for sigma belonging in S. This is the conjugacy class. Okay. And I also want to tell another notation. C of pi with a subscript S. No L here. This is the notation for centralizer. Okay. What is a centralizer? Set of all elements sigma which commute with pi such that sigma pi is equal to pi sigma, and sigma belonging to Sn is already there. So this is called the centralizer. Conjugacy class is not a subgroup, okay? You need to know that. Centralizer is a subgroup. you can easily show that identity is here. If you have two elements which are conjugating, commuting, then the product also will commute. So easily you can show that it's a subgroup. These two we will be using. Okay. Now there is now group theory recall. This have you heard of orbit stabilizer theorem? I will just write it down. We don't need the general formula, but one formula we will be using. If X is a set which acts on a group G, okay, G acts on, sorry. G acts on S, X, okay, and X dot G is defined in some, no, it's like this.
G dot X.
Okay, sorry. G dot X, sorry. The set of all G dot X, correct. Set of all G dot X for X belonging to X is called the orbit, right? Orbit of G, correct. Now what is the stabilizer? Stabilizer is set of all X such that G dot X is equal to G itself. Am I right?
G dot X equals to X.
Huh?
Orbit of X, stabilizer of G.
Did I miss something? Okay. What?
Orbit of X and
Orbit of X,
stabilizer.
stabilizer of G.
Okay, yes.
Switch X and G.
Okay, now it's correct. Okay, sorry. Huh?
In
And
the
GX
set filter
is
you have G and G.
Here G and G. Okay, sorry, my bad. G and G. Y. Okay. Here GX.
X.
Huh?
GX
Gx is equal to X for X in X. Huh?
X
No, X in X. Okay. The reason why I messed up is here we are considering X to be G itself. So what I wrote
Stab X, sorry.
stab of X. Huh? Okay, let it be. I don't want this case anyways. Okay, I'm messing up. Sorry. What I am talking today is if the every element in G, X belongs to G, can act on an element in G via conjugation. Okay, when this happens, the orbit turns out to be the class, conjugacy class, because the definitions are the same. And what is the stabilizer? Stabilizers are the thing which doesn't change. So what should happen here? Xg X inverse is equal to G itself. If you multiply by X inverse, you get this, which is same as the centralizer. So orbit stabilizer theorem tells this: the size of the orbit is equal to the size of the group divided by the size of the stabilizer, which turns out to be size of the class is equal to the size of the group divided by size of the centralizer. This fact, today I think we will use this more than 5 times, so that's why I'm writing this. Okay, the size of a conjugacy class of pi will be equal to the size of Sn, I will write n factorial itself, divided by the size of the centralizer. Okay, now I will this was half done. I will continue this discussion now. What I showed here is, if you have a permutation and if you do conjugation, the cyclic structure remains. Now I will prove the other way around. Imagine you have two permutations. One is pi, another is tau, and they have the same cyclic structure. And I will write it in a descending order. Like a big cycle on at the first, small cycles at the end, like this I'll write. Similarly, I will write the same thing for this also. Okay, let me write A1, A2, AL1, B1, etc. Okay, and here something, okay, X1, X2, and this also has the same length, Y1, Y2, dot ordered like this. I need to show that these two are conjugates of each other. How can I do that? I can define sigma, okay, I don't want this to be sigma, I'll define this tau. I can define sigma, which is a bijection which maps like this, top to bottom. Is it a permutation? Yes, because it's a map from n elements to the n elements. It's a bijection. So it is a permutation. Now my claim is sigma pi sigma inverse is exactly equal to tau. Why is this true? Same argument. When I have sigma, if I conjugate with sigma, what will happen? Let's see. Sigma pi sigma inverse, when acted on, okay, what will happen? Here I have written all the cycles. So this will happen to be sigma a1, sigma a2, dot dot dot, right? By the definition of sigma, what is sigma doing to a1? It is sending a1 to x1. So sigma a1 is x1, sigma a2 is x2. So you will get back tau. So what did I show now? If two elements have same cyclic structure, they are conjugates. If you conjugate a element, you preserve the cyclic structure. So there is a one-to-one mapping between the conjugacy class of each permutation and the partitions of n. What is a partition of n? The number of ways. Okay, the partition is you break a number into many pieces whose sum will add up to the same number n. Here, what was the partition? Here, if I see, this will correspond to 6 plus 1. This corresponds to 6 cycle and 1, both add up to 7. So the number of conjugacy classes is equal to the number of partitions. Okay. We collected a lot of facts now. Let's apply everything on a simplest example possible. Then I will define alternating groups. Then I will define ambivalent property. Then we will do something more interesting later. Okay. What is the simplest symmetric non-abelian group? S3, right? S3. S2 is abelian, so S3. Let's take that as an example. S3. How many elements does this have? 3 factorial. Let's list. E transpositions 1, 2, 2, 3, and 1, 3. 1, 2, 3, and you write 1, 3, 2. Today I will write 3, 2, 1. Just to show that these two are inverses of each other. It's okay. These are the 6 elements. Now let's calculate the conjugacy classes of all. What is the conjugacy class of E? It is the set of pi E pi inverse. E does nothing. It's just pi inverse, which is identity. So the only element you get here is identity. What is the size of this? Size is 1. What is the conjugacy class of a transposition? This is called transposition. Okay. What is the conjugacy class of this? All the 2 transpositions. 1, 2, 1, 3, and 2, 3. So what is the size? 3. Now what is the conjugacy class of this element? This is all the 3 cycles. 1, 2, 3, and 3, 2, 1. This has size 2. I want you to use this theorem and just verify this. We will be using this again. That's why I am using this theorem to show that this is true. Okay. So what is the centralizer of E element? So what is the set of elements which commute with E? That's every element, right? So the centralizer is the whole set. So the size of the set divided by the whole set will turn out to be 1. This is 6 by 6. Clear? Now let's see this. 1, 2. What all elements commute with 1, 2? Obviously identity is there. Other than identity, 1, 2 also commutes with 1, 2. So the centralizer has size 2. So the conjugacy class will have 6 by 2 size. Was it correct? Yes. Now same thing here. What all elements commute with 1, 2, 3? Identity commutes. 1, 2, 3 commutes. 1, 3, 2 also commutes. This last element also commutes because they are inverses of each other. 1, 2, 3 times 1, 3, 2, 3 to 1 is same as 3 to 1 times 1, 2, 3. So the centralizer has size 3. So this is 6 by 3. Verified, right? Proof by example. I proved that theorem. Okay. Now, this is not it. I want you to. Now we know that these two are conjugates. Why are they conjugates? Because they have the same cyclic structure. Okay, well, let's write the partition also. What partition does E correspond to? It is 1 plus 1 plus 1. Because 1 is in 1, 2 is becoming 2, 3 is becoming 3. 3 cycles. I'm okay. I want E I'm writing as 1, 2, 3. 1 cycle, 1 cycle, 1 cycle. What are the two transpositions? These transpositions are there. They are corresponding to 1 plus 2 partition. This 2 corresponds to a transposition. This 1 corresponds to a fixed point. What is this fixed point here? It is 3. Here 2 is the fixed point, like that. What is this corresponding to? 3 itself. So what are the partitions of 3? 1 plus 1 plus 1, 1 plus 2 and 3. These are the only 3 partitions of 3. So we have 3 conjugacy classes. This is also verified. Now let's find the conjugate for some examples. Only for 2 examples we will do. So you know that 1, 2 and 2, let's take 2, 3. You know that these 2 are conjugates. But via what element? How can you find that? I told you a trick also. How to find the conjugating element. Write its cyclic structure. 1, 2 is not enough. You need to write 3 also. Write 2, 3 also. What is 2, 3? And you write 1. Send this to this, this to this, this to this. That you call as sigma. So what is sigma doing? Sigma sends 1 to 2. What does it do to 2? 2 is sent to 3. 3 is sent to 1. So you can verify that 1, 2, 3 times 1, 2 times 1, 2, 3 inverse is indeed 2, 3. Okay? Nice. This is the way we can construct the conjugating element also. This element also we can construct. Clear with all this? Shall we move ahead?
Partitions you usually take in like ascending order, right?
You take in descending order. Okay, I didn't use the order. It doesn't matter. It doesn't matter. It's
Okay, that's okay.
it doesn't matter. One main thing I forgot to tell was the cycles which are disjoint commute with each other. I just forgot to tell that, but it's very obvious. Yeah, that. Okay. Now we are going to define what the alternating groups are. What is the size of alternating group? Can anyone tell?
N factorial by 2.
Very good. But this n factorial by 2 only when n is greater than or equal to 2. That you forgot. I wanted. So A0 size is 1. A1 size is also 1. These two are 1. These two are dumb examples of alternating groups which show up later. That's why I wanted to mention. Okay. These are alternating. Alternating groups are set of all even permutations. What is an even permutation? There are many different definitions. Some are very nice, but I don't have time to tell everything. Easiest way to understand is every cycle can be broken into transpositions. If you have a cycle 1, 2, 3, 4, 5, you can break it as 1, 2, 2, 3, 3, 4, and 4, 5. These two are exactly the same. 1, 2, 2, 3, 3, 4, 4, 5. Correct. These two are exactly the same. Okay. Now you count the number of transpositions. If it is even, you call the permutation to be an even permutation. If the number of transpositions is odd, you call the permutation to be an odd permutation. Now this happens to be a homomorphism. The function psi, which from Sn to the multiplicative group of 1, minus 1, such that every pi goes to sine of pi, where sine is defined as follows: sine of pi. This happens to be a homomorphism whose kernel of this sine is exactly equal to the alternating group. Forget about all these homomorphisms and all. All even transpositions form a subgroup, and it forms a subgroup of index 2. What do I mean by that? Half the elements. Half the elements are even, half the elements are odd. And if you think as transpositions, it's obvious that even permutation times an even permutation is still an even permutation. Even times an odd is odd. Odd times odd is even. These things are needed. One more thing, result I want you guys to recall is a cycle is an even permutation if and only if the length of the cycle is odd. This is very bad. Okay, so if the length is odd, it's an even permutation. If the length is even, then it's an odd permutation. You guys can see this, right? So how many elements, is this an odd length cycle? Yeah, this is an odd length cycle. How many transpositions were there? 4. So it's an even permutation. Clear? So what is A3 then? We just solved an example, right? What is A3? It's just identity 1, 2, 3 and 1, 3, 2, 1. This will be my A3. Okay. Now it's time to define something. Pi I will write as product of like cycles. I will write like this. What is pi inverse? We already did this, right? What is pi inverse? You take everything, if it is in this order, you will write it in reverse order. Okay. Reverse order, if you write like this, it will be pi inverse. Are these two having the same cyclic structure? So what is happening then? Pi is conjugate to pi inverse. This equivalence I am writing for conjugate. Okay, there is no other equivalence which I talked today. That's why if I write this, it's via conjugation only. So pi and pi inverse are conjugates of each other because they preserve the same cyclic structure. This property of a group is so good that there is a definition which is motivated from this, and that's the title of today's topic. A group G is called ambivalent if for all G in G there exists H in G such that G inverse is equal to H G H inverse. Same thing I have written in words. If these two are conjugates to each other, you call the group to be ambivalent. Are Sn ambivalent groups? Yes, because for every element, inverse also has the same cyclic structure, so it's ambivalent. So clearly, Sn is ambivalent for all n. Half the talk is done. Now our next part of the talk is, are alternating groups ambivalent? If we can finish that in next 1 hour, then it will be nice. Okay, let's see. What do you think? Are alternating groups ambivalent? See, what are alternating groups? It's the same thing, but only you have even permutations. So you have an even permutation, and its conjugation will also have the same cyclic structure. So if they are conjugates in Sn, why not in An?
Because the corresponding H might be on.
That's the point. So if in Sn, G and G inverse are conjugates because of this element H. If this H element itself is odd, then you can't use this in An. That's the problem which happens. So not all Ans are ambivalent. So what are ambivalent? So we are classifying all the ambivalent Ans today, alternating groups today. For what all n will An be ambivalent, and it's fun. Okay, it's fun to do. Now I want everyone to write. If you are writing, you write. Just have a guess in your mind. Okay, I'm pretty sure it will not be close at the end to the final answer. Just guess. For what n do you think it's ambivalent? For what n do you think it's not ambivalent? Random guess, like for even n's it's what? Yeah, A0 and A1 are obviously ambivalent. Perfect. Yeah. Okay.
A2 is not because it's cyclic.
A2 is also ambivalent, right? S2 has only 2 elements.
Sorry, A3 I meant.
A3 is not ambivalent. Why?
Cyclic. So like the conjugate is the element.
Let's see an example. A3 is not ambivalent, which is correct. What is A3? It has E, 1, 2, 3, and it has 3 to 1, right? If you take the class in A now, that's why the subscript is important. Class in A of the identity element, you get identity only. There's nothing to show here. Okay. If you take this 1, 2, 3 element, what will happen? Let's just do this. E, 1, 2, 3, E inverse. What is this? 1, 2, 3. Next, 1, 2, 3, 1, 2, 3, 1, 2, 3 inverse. What is this? These two cancel. What is this? 1, 2, 3. 1, 3 to 1, 1, 2, 3, 3 to 1 inverse. What is this? 3 to 1 is this inverse. Inverse of 3 to 1 is 1, 2, 3. So the conjugacy class of 1, 2, 3 is just 1, 2, 3. Some serious problem is happening. Now, what is the conjugacy class of 3 to 1 then? Similar, and you can also see every element we have finished. Right? So this is just 3 to 1. Are these two in the same conjugacy class? No. So the inverses are not in the same conjugacy class. So they are not ambivalent. So what was the problem happening was, these two are conjugates in Sn, because there is a transposition which can conjugate with this to get this, but the transposition is not there here, so it fails. Correct? Okay, you all did a guess, right? Okay, we can continue now.
The guess for how many?
How many? Okay, tell
What
how
is the
many.
answer? Like no, not answer. Sorry. What is the question?
For what n do you think an are ambivalent?
Is it
See,
set?
it's
Do you want
definitely
to-
not null set because a0, a1 and a2 are already there. a2 is also there. I'll just demonstrate this once, okay? What is s2? It has its permutation of two elements. It's identity and 1-2 permutation. 1-2 is anyway odd, so you throw it out. You just have identity. If you have identity, it's obviously ambivalent because its class has its inverse. So a0, a1, a2 are there. Along with this, you can guess like for even ends it's ambivalent, for odd ends it's not ambivalent. Something like that. Just have a guess. How many of you know representation theory, character theory, anything? Just 1 minute. I want to change the topic. This is just for you to motivate this definition. Okay. See, character of T inverse, an element inverse, is the conjugate. Do you know this? And character is okay. And the character is a class function. So on a equivalence class, on the conjugacy class, it takes the same value. If T and T inverse are in the same class, then I also have T inverse is equal to chi of T because they are in the same class. This will force this to be a real number. That's the motivation. Okay, in representation theory, that's how it will help. So if you have an ambivalent group, the character table will be purely real, even if you are doing representation on a vector space over complex field. So complex numbers doesn't show up. Now if I get time at the end, like last 1 minute, I will state a strongest theorem which will also tell that character table over Sn will be over integers. This is people who don't know representation theory may not appreciate this, but this is very, very strong, right? It's not so easy to do this because Sn is such a big group also, and you are getting such a strong result, which is fantastic. Okay, back to this.
If any group is ambivalent, then the table will be over Z. No?
No. It need not be. It's real. That's it. I don't know whether it's.
Oh,
Z.
okay.
There is another strong condition. If that condition is satisfied by the group, then it's true, and that condition is satisfied by Sn.
Can I take a guess?
Okay.
Transitivity.
No, nothing to do. Okay. Shall we start? Now I will break this into chapters. Okay, chapter 1, chapter 2, chapter 3. So it's a very big process, but you will enjoy it. Okay, it's nice. So, what is the problem happening? Okay, so first let's see the problem. You have a conjugacy class in S3. That conjugacy class, rather than sitting as a conjugacy class in AN, it just broke into two pieces. That's the problem which is happening, right? So first chapter is to understand why this breaking happens. Why this happens, when it happens, how to avoid it. We can't avoid it, but we need to know that when can we avoid it. Yeah. So let's start. This is called splitting of classes, okay? Splitting of conjugacy classes. When does it happen? Let's see. For this, we need to know the idea of this formula we will be using. Let me start. You have Sn, you have An. Okay, take an element in An. Let pi belong to An, and you have a conjugacy class in S of pi, and you have a conjugacy class of pi in A. What do you think is the relation between these two? This is a superset, this is a subset. Why is that so? So you have pi, take all elements in S and do conjugation. Here you have pi, take all elements in A and conjugate. So clearly all the elements you get here will be here. So this is bigger than this. And it may be equal also. That's the first observation. Next, let's do something more. Let's see the centralizer. What is this? The elements which commute with pi in S. Now you have this. What is this? Elements which commute with pi in A. What is the relation between these two? What? This is bigger than that. That's one thing, but there is more, much more. I can clearly say that this is exactly equal to this intersected with A. And the reason is, see, you take all the elements which commute. If they are odd, that doesn't show up here. You just throw them out. So you only see the intersection. All the even permutations which commute will be this. You have this relation also. We will be using this. Now, using the orbit stabilizer theorem, what is the size of this? Size of Sn, which is n factorial, divided by size of the conjugacy class, so size of the centralizer. This is the size of the class. Here what is it? Size of alternating group, which is n factorial by 2 divided by the size of the centralizer in the alternating group. Clear with these two formula? Now I will tell there are two cases possible. Case 1, case 2, and we will study both these cases properly. Case 1, when centralizer sits inside An. First I'll write it in a mathematical statement. Now I'll explain with English also. This means all the elements which commute with pi are even permutations. That's the meaning, right? If this is the case, you can easily compute this. If this happens, what is the relation between this and this? They are equal. Because you intersect with An, since everything is in An, these two will turn out to be equal. So now you use this formula. What is happening? Here you have Cs pi, here you have Caa, put it S because those two are same in the first case. What is, compare these two. One is half the other. What is half the other? I want to write this. This is equal to 2 times. Did I make a mistake? Tell me. This is smaller, so multiply by 2, you get this. Correct, na? Correct. Did you understand? I'm comparing. This is the easy case which we can understand. Any problem? Okay, should I write this? This is the size of this. This is the size of this. The only difference is by 2 here. Actually, there was Ca pi here, but I'm working in a case where both are the same. So this is true. Now there is a second case. So second case is opposite of this case. So what I should write is, there exists a tau which commutes with pi, but it is odd. But it is odd, I will write as pi does not belong to A. This is the second case I can think of. This case has a special property. In this case, the size of the class in S and size of the class in A both will be exactly the same. This needs a proof. I will prove it. First, digest both the cases. Every element is in An, easy case, you understand what is happening. Other case was, there exists an element outside An, then this is what is happening. I will prove this. For this, I will write a diagram. This will help. This is my symmetry group. Okay, it starts with identity, blah 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 blah. Every element like this. I will write. This is a set. Okay. Now half of the elements. This is An. All the even permutations. Now what I am telling is, so okay, this centralizer is also a subgroup. So centralizer contains this E. So if centralizer is inside An, that's my case 1, which is easy. Now we take the case 2, where there is a tau here, which is outside An, but in this centralizer group. Rather than writing Cs pi and all, I'll write generally. Okay, a K is a subgroup. K is a subgroup of Sn. Okay, and you have a tau belonging to K, but tau not belonging to An. This is the setup. Now what I'll prove is, the number of elements here inside An which belongs to K and the number of elements which are outside An which belongs to K are exactly the same. That's what I will be proving. First, understand what I am proving. K is equal to K intersected with AN, disjoint union, K intersected with AN complement. This is true, there is nothing more to this. This is just set theory. But now what I am proving is these two have the exact same size. For that, what do? I create a bijection. Okay, I create a map phi from this set to this set. What do? I take an element tau. No, not tau. Tau is already used. I take an element pi. I will send it to tau pi. That's it. This is a bijection. I will prove it's a bijection. Before that, let's see whether it's well defined. If pi belongs here, what does it mean? Pi is in K, pi is even. Correct? Now when I multiply by tau, tau is odd because tau is not in AN. So odd times even is odd. So this is not in AN, but it is in K. Why it is in K? Pi is also in K, tau is also in K. Since K is a subgroup, the product is in K. So this is well defined. There is no problem. Now I will show it's a bijection. Let's see pi 1 and pi 2 go to the same element. If that's the case, if tau pi 1 is equal to tau pi 2, I can multiply by tau inverse both the sides. What do I get? Pi 1 is equal to pi 2. This proves injectivity, right? I get confused. Injectivity, subjectivity, something. This will prove something. Okay, now okay, this is easy. Now surjectivity is also nice only. So take an element here and I show that it has a pre-image. How do I show that? Take some element, call it sigma, multiply by tau inverse, and I need to show that this is even, which is obvious. Why? If tau is odd, tau inverse is also odd, and it's in K. Why is it in K? Tau is in K, and K is a subgroup. So tau inverse sigma is even permutation. It's even. Why is it even? Tau inverse is odd, sigma is odd.
Sigma is odd.
Sigma is odd. I took it from here. So product is even. So that's an element here, which is sent to sigma itself. So it is surjective, it is injective. What does it prove? This is a bijection. So the number of elements here is exactly same as number of elements here. Clear? Now you are questioning what this K is. I am applying this whole theorem for K is the centralizer subgroup. I am using this theorem on that. I will prove this now. Conjugacy class of pi in the alternating group is equal to n factorial by 2 divided by, I'm rewriting that formula, centralizer in A. This was the formula. What is centralizer in A in this case? In this case, since there exists an element, it is breaking into two parts. So the centralizer in S is breaking into two parts. One like this, even guys and odd guys, and this exactly is the centralizer in A. Why is this so? I wrote somewhere this thing. Correct, and this has the same size. They are adding up to the size of this, so the size of this is equal to this by 2. Okay, you understand it? Okay, it's half of it. So this is equal to n factorial by 2. This is size of conjugacy class in S of pi and half of it. Half cancels. What do I get? N factorial divided by centralizer of S. What is this number? CLS of pi. So this and this are same, and one is the subset of other. Two sets. One is a subset of other, same size. What does it imply? CLA of pi is equal to CLS of pi. First chapter is over. So I will summarize this chapter. What is happening is, you are looking at the conjugator. Oh no, we are looking at the centralizer. Centralizer can do two jobs. One, it can sit inside AN, or it can break into two parts. If it is breaking, if the centralizer is breaking, then your conjugacy class doesn't break. It is same. The conjugacy class in S and conjugacy class in A are the same. If the conjugacy class is not breaking, if it is sitting inside AN, then if your centralizer is sitting as single entity, then your class will break into two. Remember this, okay? It's very easy to remember. If conjugacy class is breaking, centralizer doesn't break, or opposite I should say. Sorry. If the centralizer is not breaking, this will break. This will break. Okay, like that. If one breaks, another doesn't break. That's right. Clear with everything? So, now what case I need to worry? You need to tell me. See, I have a conjugacy class of pi in S. This conjugacy class contains pi inverse also, because in S, pi and pi inverse are conjugates. If this and this are the same, it means that pi and pi inverse are conjugates here also. So does it trouble me to prove ambivalency or something? No, this is nice. So good boy. I need not worry here. I need not worry. I'm writing this because there is a chance that you get confused in the next step. So that's why I'm writing. Here I need not worry. But here in this case there is a problem. You have a conjugacy class in S, but when you see the conjugacy class of the same element in alternating group, it is splitting into two groups equal size. So what if pi sits in one group, pi inverse sits in the another group, not group I should tell, another class. This is exactly what happened in our example, alternating group of A3 when we did. One class broke into two and the inverses went into different pieces. At that time you won't have ambivalence. Understood? So here I need to worry. I will be erasing, digest this factor. Splits into two halves. This part of the board I will just write the results, okay? If and only if is also there. Both the ways it's just the opposite, write the proof in the opposite direction. If and only if CS is completely contained in AN. If not, what I mean by if not, if there exists an element which is not even, then CLS is equal to CLA. And this is the nice case. Here this is the bad case. Okay. Now we can move a bit faster, okay? Take an element pi, which is in AN, even permutation. Okay? Now, my whole goal, I will tell the goal of this is chapter 2. Now my goal is to find a centralizer, so find a element which commutes with it, which is odd. Why is this my goal? If I find an odd centralizer, then it will be this case. At that time I need not worry, that's the smiley face case. So the inverses will be in the same conjugacy class. Correct? Now when will this happen? That's the question. When does the second case happen? That's what we are answering right now. First answer, simplest answer, I will write the result. Every result will be here. If pi contains an even length cycle, we are happy. Can you see why? Very easy. See, you have pi, many elements, but this has even length. Let me write A1, A2 till AL1. This is your pi. Consider this element AL minus 1 dot till A1. What did I do? Just I inverted this. I will call this sigma. What is sigma times pi? This doesn't have any other element, so it commutes. So I can bring this guy towards this. These are inverses of each other. They just kill themselves. So what I get? only this blah 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 stuff, this guys, those guys I will get here. Clear? What is pi sigma? I have pi, I multiply this from here, I can pull it there, it will again kill, I get the same. So these two are equal, right? What does this mean? Sigma is a centralizer, it commutes with pi. So sigma is a centralizer. When you have a, and also, is this even or is this odd? The length is even, so it's an odd permutation. This does not belong to an. So I just found an element which is in the centralizer, which commutes with pi. So the whole story, read it backwards now. So what happens? So the conjugacy class doesn't break basically if you go move up. So you understood this sentence? If pi contains an even cycle, then you need not worry. Why you need not worry? The conjugacy class in S and the conjugacy class in A will be the same.
Can you explain the killing yourself part?
Okay, so okay, let's write an example. Nah? Pi is 1, 2, 3, 4, 5 and 6. Let's say from S6. Let's say, okay. This is a cycle. Okay. Now this is even length, right? Now consider sigma is equal to 4, 5. Just that. Okay, 5, 4. 5, 4 and 4, 5 are same, right? Let me write 5, 4 just for clarity. Now what is pi sigma? Sigma pi or something, okay. Now you multiply this side, okay. Since 5, 4 and 1, 2, 3 are disjoint, you can bring it this side. And 5, 4 and 4, 5 kill themselves. That's the word I use, okay. So they cancel out each other, okay. So what you get is 1, 2, 3 and just 6. This is what you get. Now what happens if you multiply this side, if you multiply, it's the same thing. It will just go there, kill, and you get the same thing. So what happened? These two are same. What does it mean? And what is this? This is an odd permutation. This does not belong to AN. So if I have an odd permutation which is not in AN, then I need not worry. That's what I proved in the previous chapter. Clear? Okay. Is this a strong condition or is it very weak? It's pretty strong, right? Say take some number like 100, and if I tell you to partition 100, you need to partition without using an even number. If you have an even number, that will correspond to an even cycle, and then you know that I need not worry about that. Conjugacy classes remain the same. So only conjugacy classes with odd numbers, odd length cycles will create a problem, potential problem, but that's also not there. I'll show that now. Okay, second case. Pi contains two odd cycles. Odd cycles means not odd permutations, odd length cycles of same length. If pi, say I'm repeating the same thing. If pi has two cycles of odd length of same size, then also it is not there. Why is this true? I will show with an example only, okay, but it's not proof by example. You can do A1, A2, A3, A4 also, but it's just bad notation. That's why I will write with an example. Let pi be like this. Some element 1, 2, 3. Let me have 4, 5, 6, 7, 8. I need only odd lengths, okay? Even lengths shouldn't be there. If even lengths, I already covered it. And again 8, 9, 10, 11, 12, 13 also. Okay. Imagine this is pi. What is happening? There are two odd cycles of the same length. Now I will cook up a conjugator which is odd, and I will be done. If I have an odd conjugator, my job is done. So it doesn't split, everything is good. So what is the conjugator which I can cook up here? Like this. It's not easy to see, that's why I'm writing. Sigma. What I'll do is take the first element, swap it with the first element here. Take the second element, swap it with second element there. 6, 11, 7, 12, 8, 13. Is this an even permutation or odd permutation?
Odd permutation.
This is an odd permutation. So count the number of transpositions, it's odd. In the example I took like that, but generally it's true, right? Why? These are odd cycles, and for every element, not odd cycles means odd length cycles. For every element I have a transposition. So this does not belong to AN. This is there, and I need to show that this commutes. That's not an easy job, but I will do it in a different way. Rather than showing that this is equal to this, I will do a trick. I will show that these two are same. Same thing, right? This is easy because we studied how the conjugation works. That's why I started with telling how the conjugation works. See, has sigma anything to do with 1, 2, 3? So 1, 2, 3 is fixed. So when I do this conjugation, I'll see what happens. 1, 2, 3 stays as it is. This cycle stays as it is, but rather than 4, 5, 6, 7, 8, I will have sigma 4 going to sigma 5, going to sigma 6, going to sigma 7, going to sigma 8. If you remember how we started. What is sigma 4?
9.
Sigma sends 4 to 9. What is sigma 5? 10. So basically in this place, I get this cycle 9, 10, 11, 12, 13. In this place, rather than 9, 10, 11, 12, 13, I get sigma 9, sigma 10, sigma 11, sigma 12, sigma 13. It will be 4, 5, 6, 7, 8. Are these two same? Nice, right? So I cooked up a conjugator only. I cooked up, not conjugator. I cooked up a centralizer because sigma pi is equal to pi sigma, which has odd length. What does it mean? Then the conjugacy class doesn't break down. It will stay as it is. So it's also a happy case. Nice? Okay. Now I will prove something else. Then I will give 1 minute of break, okay? 1 minute break for everyone. Now what I am doing is, I will tell if and only if condition. Now till now I have proved one direction. What did I prove now? Okay, I will write the statement. Class in Sn splits if and only if class of pi in Sn splits in An into two different, you know the meaning of this now. Splits into two conjugacy classes in An if and only if pi contains an even class splits only. Okay, if this happens, then the class doesn't split. That's what I have. Happy faces doesn't split. So what I should tell is if contains cycles of pairwise distinct odd lengths. This is what we are going to prove now. If you have pairwise distinct cycles, then what I'm basically proving it is, in that case, all the elements in the centralizer will sit inside An. So there is no odd element which is in the centralizer. That means the class splits. That's what I'm going to prove now. Okay. This is easy to see. Okay. So I have a pi. It has odd lengths. So let me start with some numbers only. Okay. Start 1, 2, 3, and 4, 5, 6, 7, 8, and I'll write one more. I need distinct, so I shouldn't repeat the length. 9, 10, 11, 12, 13, 14, 15. Odd only, right? Okay, let this be the pi. Suppose I have a sigma. Okay, suppose I have a sigma which such that it is the centralizer. Suppose I have this. Okay, what does it do? Let's see. This is same as telling sigma inverse is equal to pi, right? Clear? So I need pi after conjugating with sigma. So tell me how sigma looks like with intuition. I will explain. So I will write pi again. Okay, pi again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. Now see one, observe here. I need a sigma. What does sigma do? Sigma is mapping from here to here. That's what we were doing previously, right? That's how conjugation works. I want, when I do that, I should get back pi itself. So I should get the same result after conjugation. How, what kind of sigmas can do the job? The first thing is identity. Clearly identity does the job. But I need something interesting. What interesting can do this job? Okay, I will write. It will give a hint. Rather than writing 1, 2, 3 as 1, 2, 3, I will write as 3, 2, 1. 2, 3, 1. Are they same?
Yes.
Rather than writing 5 like this, let me choose, let me start with 7. 7, 8, 4, 5, 6. I will start with 15 here. 15, 14, 13, 12, 11, 10, 9.
No.
Hey, oh, what?
15,
No.
9,
Sorry, that's very bad. 15, 9, 10, 11, 12, 13, 14. Is this same as pi? Or is there a difference? It's same as pi, right? Now, if my sigma sends 1 to 2, 2 to 3, 3 to 1 like this, then if I conjugate, you know how conjugation works now. So if I conjugate, from here I get this thing, which is same as pi. So at that time, my sigma will be a centralizer. Clear with this? Is this the only way you can do? There are many more ways. I can send 1 to 3, 2 goes to 1, well, this goes to this. This is also a possibility. So basically what I am doing, rewriting this in a cyclic manner. So this can be proved rigorously, but easy. This is the easiest intuition you can have. So all the elements which are in the center, which commute with this pi, are generated by these 3 cycles. Generated. It's a subgroup generated by these elements. See, 1 going to 2, 2 going to 3, 3 going to 1. That sigma is exactly this cycle. Then you have this cycle, and you have this cycle. This is the proof. Okay, there is nothing more to this. You can see right now. Take 1, 2, 3. Put it. What will 1, 2, 3 do to this whole cycle? What will it do? 1, 2, 3 will go here. It will make it 1, 3, 2. It will do. Okay. Now multiply 1, 2, 3 from here. What will happen? It's the same thing. So 1, 2, 3 is a centralizer. Similarly with every cycle. And you can also have this cycle multiplied by this cycle, or this cycle to the power something. So it's a subgroup generated by this. Clear? What is this, even or odd? Even odd length, but even permutation or odd permutation? Everything is even permutation. If I raise to a power, I'll get even permutation. If I multiply them, I'll get even permutation. So every centralizer is even. So that is the first case, right? Centralizer sits inside here. That's the case we are talking about. And this is a smiley face or a crying face? Crying. Here we have a problem. So I will summarize. You have Sn. You see a conjugacy class in Sn that can split or it can stay intact. It stays intact if you have an even length cycle, or if you have 2 odd length cycles with the same odd number. But if not, if the pi is such a way that all the cycles have distinct odd lengths, then you need to worry a bit.
And now what we have done is that we are just saying that this kind of is gonna be centralizer. How are you gonna say that this is the only?
Because after doing this conjugation, you are supposed to get pi itself. So the cyclic structure shouldn't get ruined, because conjugation doesn't ruin the cyclic structure, and it should be the same pi itself. So there can't be anything other, because we know exactly what a conjugation does. That's why I started the class by, not class, sorry. I started the talk by explaining what the conjugation does. Clear? Now, okay, I can finish in 20 more minutes. So, like 2 minutes break. May I just stare at this? Okay, stare at this. Chandrashi, this is what he tells. by that time you guys can tell your guesses. That's very it will be fun, yeah. Any guess? Gaurav? No.
Is equal to 2 or 3 mod 4. Then it's
Oh, nice.
Not
Okay, nice. Good.
something.
Anyone else? Okay.
Primes of the form 4k plus 1.
Primes of the form. Okay, nice.
Is the guess close?
Very far, yeah. Both are very far. Okay, I'll just give a spoiler.
No.
Both the classes, both the numbers you told, na? There are infinitely many numbers like that.
Yes.
But there are only finitely many alternating routes which are ambivalent. And those finitely many numbers are there, na? They're so bad, there's no pattern with them. That's also a fun thing. Pairwise distinct. Okay, last 2 chapters, we'll be done.
How many of these are there?
Huh?
How many of such ambivalent alternating groups are there?
0, 1, 2, including 0, 1, 2?
Sure.
They're so bad. 0, 1, 2. 7.
Five.
7, 7.
Okay, 0,
Okay.
0, 1,
What was 0, 1, 2?
then 5.
Okay.
Then there's 6.
Okay.
Again, you cannot break it. No, you can. 5 and 1.
Yeah.
7 you cannot break down, I think. Yep.
Okay, you guys are missing something. Just because a class breaks doesn't mean that it won't be ambivalent. A class can break, still inverses can stay in the same class, right? That we didn't see now. Correct now. There is one more complication. Okay. Now the next chapter is about that. Whenever it breaks, whether inverses stay in the same class or whether it stays in a different class. Okay. Now we are talking about splitting cases only. The partitions where the class splits are called as splitting partitions. Obvious word, right? So it will be or distinct odd numbers, basically distinct odd numbers with sum up to n. Okay. Now we will start about that topic now. Okay, I don't want to use this letter, but this letter is used in the textbook. Exactly. Well, okay. This is okay. I will give a permutation, which is called standard conjugator. Very fancy name. Okay, it's called standard conjugator. Basically, we are cooking up a conjugator. Okay, nothing more we are doing. The way we cook is the nice thing to see. I need a pi. I don't need it to be a non-splitting case. I want it to be a splitting case. So odd lengths. Let me write numbers. Okay, but when I write numbers 1, 2, 3, 4, don't think I'm using an example. Just you can write A1, A2, A3, A4, and you can do the job. But too many numbers, it will be bad. That's why I just write this. 2, 3, 4. This is an odd cycle. And also it need not be 1, 3, 5 and all only. It can be anything. I can just have 5, 6, 7, 8, 9, 10. How much is this? 11. Okay, let pi be like this. Okay. Now how I cook my xi is that if 1 is there, let it be as it is. Now this 2, 3, 4 is there, na? I will swap the first element with the last element. Rather than this, I should do it more general only. Imagine it has a lot of cycles where A1, A2, L, where L is odd, okay? Li I will put. L1. Now B1, B2 till BL2. Li's are odd and distinct. This is the case we are talking about. So this is how I cook. A1, ALI1. A2, AL1 minus 1. No, not like this. Correct. A3, L1 minus 2. What am I doing? I'm swapping these two elements. Like these two like this, these two like this, these two like this. Okay? I will do this for everything. For B1, B2 also I will do the same. B1 and BL2 are swapped. B2, BL2 minus 1. Sorry, BL2 minus 1 are swapped. Like this. And I create such a such a permutation. Can you see now that if I conjugate pi with this xi, I get pi inverse. Again, you use the fact. How does the conjugation works? This cycle remains as that cycle, but xi acting on each element. Xi acting on A1 goes to xi acting on A2, goes to xi acting on dot 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 dot. Xi acting on A1 is AL1, so it starts with AL1, and now xi acting on A2 is AL1 minus 1. Dot 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 dot. At the end, this will be A1. What is this? I just reverse the order, right? So it will be inverses of each other. Clear? Nice idea, right? Now what I claim is, if xi is even permutation, then pi and pi inverse are conjugates in A. This should be obvious. If it is even, then xi is in An. So I can conjugate pi with xi now because it's an even permutation. When I conjugate, I am getting inverse. So even if this splits the conjugacy class, inverses stay in the same conjugacy class. That's the nice thing. So just because it splits doesn't mean that pi will go one side, pi inverse goes one side. That happens. In the case A3, that's what happened. But some cases it won't happen. When is the case that won't happen? This is the case. When your xi is even, then these two are conjugates. Clear? When will xi be even? This is where you use like elementary number theory. Not elementary number theory, not just that fancy stuff. Okay, see, I will tell you this. These are odd numbers, right? Odd numbers can be of two forms. 1 modulo 4 or 3 modulo 4. Imagine it's 1 modulo. So people are scared with word modulo. Just 4k plus 1, okay, for some k. That's what I meant, okay? Of these forms, like 5, then it's 9, blah, 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 blah. So if the length is like that, how many transpositions will it give? See, it has odd numbers. I'm pairing up. The middle element will stay as it is, right? It's not changing. I don't do anything to the middle element. So forget about the middle element. Then how many elements you have? 4k. And 2 you are pairing, so it's dividing by 2. So it will be 2k. So this produces 2k transpositions. 2k is even or odd? Number. The number 2k is even. Okay, the number 2k is even. So it corresponds to even number of transpositions. So xi will be even. That's not a problem. When does the problem occur? When the length is of the form 4k plus 3. Then what will happen? If I see how many transposition it produces, 4k minus plus 3 minus 1, which is 4k plus 2 divided by 2 will be 2k plus 1. Is this even or odd? This is odd, right? This is an odd number. So this produces odd number of transpositions. So that may cause xi to be odd. So what is the condition now? The number of cycles which produces odd number of transpositions should be even. Okay, I'll repeat. There is a cycle. It produces odd number of transpositions. There is another cycle which produces odd number of transpositions. Odd plus odd is even, correct? So I need the number of cycles which produce odd number of transpositions to be even for xi to be even. Xi to be even permutation. Now I will write this. So if number of cycles with length how much? 3 modulo 4 is even. Which is even? The number if it is even, then xi is even. What does this tell? If this is the case, then pi and pi inverse are conjugate in An itself. And what is the conjugator? That will be our xi itself. Clear? Once I make a claim, I need to make it if and only if. That's the next statement. So what I need to prove now is if my xi is odd, then pi and pi inverse can't be conjugates in AN. Now I will do some manipulation, okay? Manipulation of letters. Okay, it will be nice. Let's see. Pi splits. I just read this. What do I mean by pi splits? It's made up of cycles of odd lengths which are distinct. That's everything is there. Okay, that's the assumption. I start from there. And suppose xi is odd. My claim is this implies that pi and pi inverse are not conjugates in AN, obviously, because in Sn they are conjugates. We know that. In AN they are not conjugates. This is my claim. How do I prove? The best method of proof. What is that? Proof by contradiction. Suppose there is an element. Suppose sigma. I need that to be in AN because I can't conjugate with an odd element to get an inverse. That's invalid. So imagine I have an even permutation such that when I conjugate, I get this. Suppose this is true, then I get a contradiction. Okay, now this is nice. I multiply sigma inverse. Pi is equal to, okay, you guys tell. If I multiply, what do I get?
Sigma inverse.
Sigma inverse, pi inverse, sigma. And I cooked my xi in such a way that xi pi xi inverse is equal to pi inverse. This is by construction. Now, rather than writing pi inverse, I will write it as this. So this is equal to sigma inverse xi pi xi inverse sigma. And this is same as sigma inverse xi. I will group this pi. This is sigma inverse xi inverse sigma inverse inverse. Okay, you know what I am doing now. So this is pi. So inverses, you know, it will flip, right? So it is sigma inverse xi whole inverse. So this inverse will move to this first, then it will move to this. Correct? Now I have this element, I have this element's inverse. Now I will send this, I will multiply this both the sides. So what I get? Pi multiply this sigma inverse xi will be equal to sigma inverse xi pi, and this will tie off. What did I show now?
Sigma inverse xi is a
Sigma inverse xi is a commutator. It commutes. So it is in centralizer. This is what I proved. What is sigma? Sigma is an even permutation. So sigma inverse is even. Xi was odd. So the product is odd. But we started with the claim that all the centralizers are even. And a contradiction. How was this? This was nice, right? This is so cool. Okay. So what did I show now? This is if and only if. Xi is even implies these two are conjugates. If not, then they are not. Okay, time to finish, right? Let's finish off everything. Now those finitely many we need to break. Theorem of the day. Next. Tell something now. 7. Okay. Next.
23.
Next.
23.
Oh, 23. Next.
What is that in the middle? A0 or what?
10.
No, 5, 6.
6 is 6. Next is 10. Next.
19.
17.
15.
104.
Oh, that's the close. Yeah, 14. Are the only ambivalent groups. Alternating groups. Nice theorem, right? Any pattern can I see 2, 5, 6, 10, 14, nothing? Okay, I'll show the pattern. You will be like, oh, nice pattern you will tell after this, okay? These are the only alternatives. Let's see. See, look at the sizes, okay? Sizes. This has only identity. This has only identity. This has, S2 has 2 elements, but if you take only even, it also has identity. So these 3 are boring only. That thing is there. A5. What is the size of A5? It is 5 factorial by 2, which is 60. Such a big group, and I'm proving that it's ambivalent now. Okay? And this is how I do. Tell me all the partitions of 5. Come on. 1 plus 1 plus 1 plus 1.
4, 1.
4 plus 1.
Let's start from small. 2 plus 1 plus 1 plus 1. Next.
2 plus 2 plus 2
2 plus 2 plus 1. 3 plus 1 plus 1. 3 plus 2. 4 plus 1.
5.
Clear? Actually, all these classes are not even, like conjugacy classes won't even show up in AN. Because for example, this corresponds to identity, right? This corresponds to identity. This corresponds to transpositions. Transpositions are not at all odd, but let's forget about everything. Let's not see whether it's in AN or not, anything. I have these things and use these facts. That's why I didn't erase this. If it has even cycle, I can just I need not worry about it because it doesn't harm me. Ambivalence is preserved. So all the elements which have even length cycle, I can just kill. I need not worry about them. Okay, these I need to worry. But if there are 2 odd numbers which are same, then also there is no problem. So this doesn't create a problem. This doesn't create a problem because 1 and 1 are same. So what is the problem creator here? 5. So what does that mean? What does this correspond to? A 5 cycle. So pi, let's take in AN, it's 1, 2, 3, 4, 5. This is the problem creator I have. But this creates a problem because the conjugacy class, if you see the conjugacy class in S and if you see the conjugacy class in A, they are not the same. It's broken into 2 pieces. So that's a potential problem. But there is no problem because consider xi, which sends 1 to 5 and 2 to 4. Is this even? This is even. So is it in AN? Yes. If you conjugate pi with this guy, what do you get? 5, 4, 3, 2, 1, and this is this. So A5 is ambivalent. Understood? So there is a better way to tell this. We wrote this, right? We wrote this. So the number of cycles with length 3 mod 4 should be even. So here it was 5. Is 5 3 mod 4? No, so the number of cycles with 3 mod 4 is 0 and 0 is even. So this is ambivalent. This doesn't create a problem. From 10 onwards, we can't write all the partitions and do. That's why looking at the number of 3 mod 4 elements and seeing whether they are even or not will do the job. So A5 is ambivalent. Clear with that? Next is A10, right? Now I don't want to write all these things because I think there are 42 partitions for 10. Okay, and it runs like for 100 it will be like around 1 million or 1 billion. The partitions will blow up. Right? So for 10, tell me those partitions which may create a problem. So it should be distinct odd numbers and it should be that's it, distinct odd numbers. So 1 plus 9 is already there. Is there anything else? 7 plus 3 is there. Anything else?
2, 7, 1.
2 is even.
4. Oh, every should be.
Only these two, right? These two are the potential problem creators. I'm not telling that every element in A10 looks like this. That's not what my claim is. But only elements with this cyclic structure may split. Everything else won't split. So these are problem creators. Okay, which one is 3 mod 4 here? Is this 3 mod 4? No. Is this 3 mod 4? No. So the number of 3 mod 4s is even. Or other way to see it is take a 9 cycle and if you keep on switching, how many switches do you want? 4 switches. So 4 switches is even. So xi is even. That's another way to see. But since we proved that 3 mod 4 result, let me use that one. 7 plus 3. Is this 3 mod 4?
Yes.
Is this 3 mod 4?
Yes.
So number of 3 mod 4s is even. For this I want to write an example because it's nice. 1, 2, 3, 4, 5, 6, 7 and 1, 2, 3. First, stop. See, what am I doing? 8, 9, 10. First of all, is this in AN? Yes, because odd length is even, but since definitely it is in AN. Now I want to create this will split also by all the theorem. No, we know that this will split the conjugacy class, but still inverses are in the same conjugacy class. That's because for this, what is the standard conjugator? tell me, how did I cook it? 1 7 2 6 3 5. Now this will reverse this. There is a problem. What is the problem? There are odd number of the odd many numbers, but that problem will be resolved when I do this. This will have 8 10. Now xi belongs to AN, and we have xi pi xi inverse is equal to pi inverse, implies pi is conjugate to pi inverse in AN, and this is for all pi like this, implies A10 is ambivalent. Nice proof. Oh, 6 I didn't do. You guys didn't remind. Okay, for 6 what is the partition? Odd numbers, only odd numbers. 5 1 only. 3 plus 3 doesn't work. So it's only 5 1. And there is nothing 3 mod 4. That's it. Easy. 14. Let's start from the top. 13 plus 1. 11 plus 3. Then 7 plus 5. No. 9 plus 5. 7 plus 7 doesn't work. Are these the only partitions? Can I have 3 odd numbers which add up to 14? That's impossible. Odd plus odd is not even. 4 odd numbers takes the least case. 1 plus 3 plus 5 plus 7. It will go above. So these are the only splitting partitions. 1 is not 3 mod 4. 13 is not 3 mod 4. It's 0. Done. 11 3. 3 is 3 mod 4. 11 is also 3 mod 4. So the number of 3 mod 4s is even. So it's ambivalent. So basically the conjugator, the standard conjugator will be even. 9 5. Nothing is 3 mod 4. Done. Are we finished? Huh?
Why are these the only
Only part. The only part if we talk, it will be done. And why are these? Now you will see a pattern with these numbers. Very bad pattern. Take any n. Okay. Every number can be of only 4 forms, right? Is there any other way for k belonging to natural numbers? This is the only way, right? For this, consider the partition 4k plus 3 itself. Okay, this partition let's consider. Okay, you are understanding, right? So a partition like this, how many cycles are there which are 3 mod 4? 1. 1 is odd. So this can't be ambivalent. That's why A4 is not ambivalent. No, not A4. A3 is not ambivalent. You can see now everything will connect now to the A3 was not ambivalent because what was the problem creator? 1 2 3 was the problem creator. That 1 2 3 corresponds to the cycle, this cycle only, right? So 1 2 3 was a problem creator. So if you create the standard conjugator, what will be the standard conjugator for this? 1 3. So if you do conjugation with 1 3 inverse here, you get 3 to 1. But the problem is this is odd. So everything is connecting now. So for last case, it's very easy. Now that's the whole idea. Now I need to create the partitions for everything and show that the number of lengths 3 mod 4 is odd. That's all. Let me see. I don't want to refer my book. I can see that, but does this work? Tell me. 4k minus 1. Okay, 4k minus 1 is 3 mod 4. Modulus is nothing big. Okay, it's easy. So 3, correct, right? This is 3 mod 4 and 1. You have this. So it will show that no 4k type elements can be ambivalent. Let's say A4 is not ambivalent. Okay. Now I will show that 4k plus 1 can't be ambivalent. How can I do this? Okay, first I think I remember this, so I'll write this. 4k minus 4 minus 3, which will be minus 7 and a 5 and a 3 and a 1. Add this up. 7 plus 5 is minus 2 plus 3 is 1 plus 1. Okay, correct. This is a partition, right? This is not 4 mod, this is not 3 mod 4. This is 3 mod 4. This is not 3 mod 4. This is also not 3 mod 4. Why is this not? This is what? 3 mod? No, this is
one mod.
1 mod 4, right? So the number of 3 mod 4s is still 1. So this will create a problem. So this can't be ambivalent. Now you will be thinking there is something here which looks like 4k plus 2. What is that? 10. 10 or 14 also. 10 and 14 and 6 also. Yeah. All these three things are 4k plus 2. But why am I saying that this works? That's because it's not
equal to.
Yeah, exactly. So when k is equal to 1, this doesn't even make sense, forget about it. When k is 2, I get 1 and 1 will be the same. So there's no problem. That's why it's ambivalent. When k is 3, this is 12 minus 7, which is 5 will match. So this is only true for k greater than or equal to 4. So for all those, correct na? For 4, what will I get? 16 minus 7. Okay, for that it works. Correct? For the middle one, there is something similar. Okay, I'm not able to recall. 4k, can you see 4k minus
5, 4k minus 3.
4k? Tell you, it's
1,
easy.
5 and 4k minus 3. 4k minus 6.
6, no.
Sorry, yes.
Huh?
1, 5 and 4k minus 3.
4k minus 3, 1 and 5. This is too much.
Yeah, I mean the 3 can be made into a 7.
Okay, okay. Is that the thing?
No.
Hey, why should I waste time? Okay. 4k minus 3, 3 and 1. It was so simple. What then? So, it adds up to 4k plus 1. Now, is there anything like 4k plus 1 here? Yeah, 5 is 4k plus 1. But it's not creating a problem because
K can't be 1.
k can't be 1. If k is 1, there's a problem. So k is greater than or equal to. Okay, this is the only pattern I can see in all those numbers. So I have partitions for every other numbers, but if you plug in some values, 2 numbers will be same. That's why these are surviving. Otherwise, these also will die. That's the thing. Okay. So we proved something which you will never use in life, but okay, just for information, it's very nice. Huh? These are the only ambivalent groups. Okay, nice. Before finishing, now 2 minutes, I will write a theorem. I won't prove this because I don't know the proof. If G is finite group, finite group, and for any G in G, and for any M belonging to natural numbers such that M and the size of the group are co-primes, GCD is 1, and G is conjugate to G par M, then character table, this is these people, what representation theory people, character table of Sn, representation of Sn will be over Z
You meant character table of G.
of G will be over Z. Now the whole ambivalency thing was true for, it would tell that it will be over R, reals, there won't be any complex numbers. Now I can tell it will be over Z also. And the fun thing is this big condition is true for Sn. and you can see that. It's not direct. Imagine I have 1, 2, 3 and I have 4, 5 and this is in S5. What is the size of S5? 120. Now it's not guaranteed that kth power for mth power of this guy will preserve the same cyclic structure. That's not necessarily true. Why is that not true? Just take an example. Square this. What do you get? 1, 2, 3 will turn out to be 1, 3, 2 because 1 goes to 3, 3 goes to 2 like this. What will happen to 4, 5 when you square it? It will be identity. 4, 5 is identity when you square it. So these two are these two conjugates? No, it's not sure that pi and pi par k are conjugates to each other in every case. But I can guarantee this whenever these two are co-primes. So here the problem was 2 was not co-prime with 120. So 120 is product of all the numbers less than 10. That's the idea here you are using. So what can be the length of this? Some number less than or equal to n, right? What can be the length of this? Some number less than or equal to n. Now since n divides this, because this is n factorial, since n divides this, if, what should I tell now? Oh, any number less than or equal to n also divides that. So if it is co-prime, you are not raising to the power which kills this level, which makes this identity. So that number when you put a power k, this will still be a 3 cycle. So cyclic structure will be remained. So the G and G par m will be conjugates, which implies that character table will be over Z. So every irreducible character of Sn will have all integers in the matrix. It's a square matrix, right? Number of irreducible representations and number of conjugacy classes are the same. It will be a square matrix with integers and with the dimension partitions of n. Finish. Thank you.